Alright, in this video, this is the second of two videos. This section is on solving exponential and logarithmic equations. And in fact, we know that exponential functions and logarithmic functions are opposites. And so we tend to do the opposite using, like if we're solving a logarithmic equation, we're going to end up a lot of times writing those as exponential functions. And the same was true when we were working with exponential equations. So let's go ahead and get started. So for this first problem, we have the log base 5 of x is equal to 3. So this is just a basic logarithmic equation, and it's got the basic three parts: the base, the exponent, and what I call the answer. And so it makes a lot of sense because we really don't have any way to solve this for x other than why don't we try changing it to exponential form. So this would be 5. So kind of like what we were doing with, well actually it's really the same as what we were doing with exponential functions. We're going to change to the other form. So let's go ahead and do that. We get 5 cubed equals x, and this is quite easy now. It's just 125. Let's look at number 2. Actually, before I do that, let's check this. So if you plug the 125 in, 5 to the the log base 5 of 125 is 3. That's true because we know 5 to the third power is 125, and so it does check. Let's move on to the next problem. Natural log of x is equal to 3. So very similar to what we just did. Now recall our base here, because it's a natural log, is e. And so we'll change to the other form. So again, you may want to shut the video off and try it yourself, and then check your answer. Alright, so you're going to get e to the third power is equal to x. And again, we can throw that into our calculator. You do second ln, and you'll be able to find the third power of e, and it's 20.0855. Again, this is quite easy to check. Natural log of 20.0855. You can actually put that right into your calculator and you should get 3. Alright, let's look at number 3. Log base 2 of 4x plus 1 equals 5. It's really just more of the same, but it's not one of our special cases. This is a base 2 log. So again, we'll switch forms, and when you do that, you get 2 to the 5th power is 4x plus 1, but 2 to the 5th power is 32. So now we just got to solve this two-step equation. We're going to have to subtract 1 on both sides. We get 31 equals 4x, and we'll need to divide each side by 4. Our answer is 31/4. So this one takes a little more work to check, but it does work. So if you plug in 31 over 4, notice 4 times 31 over 4, those 4's are going to cancel, and you get 31 plus 1. You're going to end up with 32 here. So the log base 2 of 32 equals 5. And again, if you put it in the other form, or if you think about it, it's the base of 2 to the exponent 5, or 2 to the 5th power, equals 32, and that is true. Alright, let's look at number 4. So now it's really just more of the same. It's just somebody messed things up a little bit here. We've got way too many parts, or at least a couple too many parts anyway. I'd like to have just the ln of x equals 6. So, and remember our base is e here, so we've got an extra number there. We got the 3 there, and we got the 7. So we're going to have to divide by 3 to get rid of that 3. We're going to have to subtract 7 on both sides to get rid of the 7. In a situation like this, we always add or subtract first. We get 3 times the natural log of x is equal to -1. So we're almost down to an equation like what we were solving in the last 3 problems. Divide each side by 3 and you can get rid of that 3 since it's 3 times the natural log of x. The 3's cancel, you get natural log of x is equal to -1/3. So there's your 3 parts. Remember, your base is e, so we know e to the negative 1/3 power is equal to x. It's just switching forms. And now you just need to put that into your calculator. Be careful to use your exponent button, the caret symbol, and -1 divide 3 in parentheses, particularly if you're using a TI-83. So you should get about 0.7165. And again, this is quite easy to check. If you plug this into your calculator, you should get it that it equals 6. So you can verify that if you'd like. You certainly should be able to do that. Number 5. So this is definitely different. Notice though we have a sum of logs on the left side. And in fact, if we could make this a single log, we could make it look kind of like the other ones we've been doing where it has the 3 parts. It's going to look a little more complicated, but it's still going to have the 3 parts. So remember, we've got 2 properties we can use for a case like this. We're going to end up using both of these. In this case, we have a sum of logs, so we're going to use the product rule. But there's also going to be problems where we'll be using the quotient rule. So you want to keep these in your mind. It's one reason why I want you to memorize these, so that when you run in a case like this, you know that you can combine those 2 logs into 1. So this will be the log of the product of x plus 6 and x plus 4. And that's equal to 1. So now you still have base, exponent, answer. You got your 3 parts. It just looks a little more complicated. So let's go ahead and write that. And we're going to have to FOIL. We got some work to do. This is basically a quadratic equation in disguise. If we FOIL the right side, and we don't really need that 1 on the 3. And let's see, let's finish that. We can subtract 3 on both sides. The 4x and the 6x are like terms. So let's clean this up a little bit. We get 0 equals x squared plus 10x plus 21. Remember, with quadratic equations, we want to get 0 isolated on one side. So that's what I've done here. And you also want a positive x squared term, and you want then your x term and your constant, which is exactly what we have. All right, so now you should be thinking AC method. We need 2 numbers that multiply to 21 and add to 10. And so that's going to be 3 and 7. And since this is a 1x squared, we can go ahead and plug those numbers in here. And so that factors as x plus 3 times x plus 7. We're going to get -3 and -7. Now, the problem here is, and actually this is the first time we've run into this, when you're solving logarithmic equations, there's one thing you've really got to be careful about, or you got to watch out for. Let's think back to the graph. In fact, we could look at the graph of y equals the log base 3 of x. So you may want to try graphing that from memory, or you should be able to graph the basic graph, and then turn the video back on. So you should get a graph that looks something like that. Remember, exponential functions, we have exponential growth or decay, and they go through the point 0, 1. With logarithmic functions, which are the inverse, we end up going through the point 1, 0. And this is the basic shape of the most basic logarithm or logarithmic function where the base is greater than 1. This is the graph I want you to know. This is the one that you should know. So our domain here, you can see, is 0 to infinity, and we've discussed that before. But think about what that means. The domain is the set of all the x values for this function. So if you think about it, it's the values that we can plug in for x. And that includes anything from, well, actually greater than 0. So another way to write this is just to say that x is greater than 0. So what that means is we can't take the log of 0, and we can't take the log of a negative. we have to take the log of a positive number. That's the only thing we can take the log of. So that's the main thing you want to watch out for. It's a good idea to always check your answers with these, but the biggest thing to watch out for is that you're not taking the log of a negative. Alright, so let's try plugging in -7. This is, you're going to see real soon this is a problem. Because notice log base 3 of -7 plus 6, that's the log of -1. And you could try that with a regular base 10 log, and if you take the log of 0 or a negative, it's going to give you an error message or domain or something, some kind of error message. So anyway, the -7 doesn't work. But if you plug in -3, this will be the log base 3 of -3 plus 6, which is 3. And -3 plus 4 on the other log, we're going to get 1. So if you look at the first log, it's the log base 3 of 3. So remember, a logarithm is an exponent. In this case, it's the exponent you put on a base of 3 to get 3. That would be 1. On the other one, you have log base 3 of 1. So what exponent do you put on a base of 3 to get 1? Well, that would be 0. And so 1 plus 0 does equal 1, and so that does check. So our only, whoops, let me go back. Our only answer here that works is the -3. All right, let's move on to number 6. So notice here, this is very similar to what we were just doing. The only difference is we have two logs on the left and they're subtracted. So we have a difference of logs. That means we can actually use the quotient rule and write x plus 2 over x minus 1. So again, all we're doing here is using the quotient rule. And now we have our base of 4, our exponent of 1, and the answer of x plus 2 over x minus 1. Let's write this in exponential form, just like we've been doing with all the other problems. And I'm going to get rid of the 1. And this is a rational equation, so we want to clear fractions. We'll have to multiply each side by -1. So notice on the right, we're going to get x plus 2. Of course, we've got to multiply the other side by x minus 1. Over there, when we distribute, we'll get 4x minus 4. We need to subtract x on both sides. And we'll get 3x minus 4 is equal to 2. So this is a two-step equation. You should add 4 to both sides. Get 3x is 6. So finally, we get x is equal to 2. So you can certainly see that if you plug in 2, you're not going to be taking the log of a negative, because you're going to get 4 on the first log and you're going to get 1 on the other log. So those are numbers that are positive. We can take the log of positive numbers. If you check it though, which isn't too much trouble, notice I went ahead and plugged in the 2. So this will be the log base 4 of 4 minus the log base 4 of 1. And we want to know if that's equal to 1. Well, for the first log, your base is 4, the answer is 4. Again, what exponent, that's what a logarithm represents, what exponent do you put on a 4 to get an answer of 4? That would be 1. And what exponent do you put on a 4 to get, or to put on a base of 4 to get an answer of 1? That would be 0. So 1 minus 0 is 1, and again, this works. All right, let's go ahead and look at number 7. So I hope you can recognize that this one is a little bit different. In fact, so far we've been switching forms. That was our big strategy. Sometimes we had to do a lot of work or some work before we could do that. Or sometimes there was a lot of work involved once we changed it to exponential form. But nothing's been like this. So I want to go back to, I want to look back at a couple of things here. First of all, everything else we've done, we've been changing forms. So that's one of our techniques or one of our approaches when we're solving logarithmic equations, similar to what we were doing when we were solving exponential equations. Now, the other thing, well, actually, I'll show you an example here. Remember, if we had b to the m equals b to the n, then we knew that m would equal n. And so if we had a problem like 2 to the x plus 3 equals 16, we could get our bases equal. So I'm sorry, what I'm doing here is I want to lead into what we're going to be talking about with this other technique. Changing forms is what we've done so far. Now we're going to do something different. Something similar to what we were doing previously with a problem like the one I'm doing right now on the left here. So we would get equal bases here, right? And we could write 16 as 2 to the 4 power, or 2 to the 4th power. Once we have equal bases, we can set our exponents equal. That's the only way these two powers of 2 could possibly be equal. And so when we do that, we get negative 1. Oh no, actually that should be 1. All right, so in a similar way, we have another property that we're going to use with these. So basically, the second approach is when we have basically log equals log, and the bases are the same. So if you have two logarithms that are equal, and the bases are the same, then that m must equal n, or those inner parts must be equal. At least that's how I say it. So we want to set the inner parts, or the insides, equal. That's how we're going to approach these. So it's very similar to what we were doing when we were getting equal bases with exponential functions. So let's go ahead and look at number 7 now. Actually, another way to say this in short is just equal parts. So if you look at number 7, don't you have log equals log? Both of them are base e. They're natural logs. So doesn't that mean that x minus 3 has to equal 3x plus 5? That's the only way that these two logarithms could be equal. If they're both base e, these other inner parts or inside parts must be equal. So again, we have equal parts, or the insides are equal, however you want to think of it. So let's go ahead and set them equal. So we just need to get x on one side. We'll get negative 3 is equal to 2x plus 5. And then we'll subtract 5. We're going to solve this two-step equation. And we get x equals negative 4. However, we do have a problem here. When we go to check this, notice natural log of negative 4 minus 3. We're going to be taking the natural log of negative 7. As soon as I see that, I know this isn't going to work, because you can try it. If you take natural log of negative 7, it's going to give you an error message because you can only take the log of a positive number. So our one and only solution didn't work, so we have no solution here. And don't forget, the other way to write that answer is using the empty set notation. All right, let's move on to number 8. So this is kind of a combination of things we've already done. Notice if we could just make one log out of the left side, then we would have log equal log. And so then we can set the insides equal. So let's go ahead and do that. Let's use the product rule and make the left side into one log. So again, the sum of the logs becomes the log of the product of x and x plus 4. On the other side, we still have log of 12. So these are both base 10 logs, or what we call common logs. So the insides must be equal, the inner parts. So x times x plus 4 has to equal 12. So again, this is FOIL in disguise. I'm sorry, it's not FOIL in disguise. This is actually a quadratic equation in disguise. So let's distribute and move that 12 over, get rid of the 12 on the right side, get 0 on that one side. And then we can use the AC method to graph this. So we need two numbers that multiply to negative 12 and add to 4. And as soon as you get to 2 and 6, you'll see that that's going to work. We're going to need to make the 2 negative. Notice negative 2 plus 6, or times 6 is negative 12, and negative 2 plus 6 is 4. So this is a 1x squared, so we can throw those numbers in there. And when we solve for x, we're going to get 2 and negative 6. Now, think about the negative 6. If you plug a negative 6 in here, you'd be taking the log of a negative. So that's definitely not going to work. And you could verify that the 2 actually does work. And notice here you end up with the log base. The log of 2 plus the log of 6 equals the log of 12. Using the product rule for logs, you'd get the log of 2 times 6, which is 12. And so this is definitely equal. You can also check this on your calculator since it does base 10 logs pretty easily. Alright, we got one last problem. So on that last problem, 2 was our only solution. Alright, so this is a lot like what we just did, but instead of the product rule, again we'll be using the quotient rule. So let's go ahead and combine the left into 2 logs using the quotient rule. And again, the 2x plus 1 should be in the numerator, the x minus 4 should be in the denominator. The order does matter. So notice these are both base 5 logs. As you're doing these kinds of problems, you got to be careful. Make sure you always use your base. Don't lose your base. Keep the base, because the bases do have to be equal in order to do what we're doing here. So now again, the inner parts are equal here. And so we're going to set them equal. And again, I want to remind you, we only do that when we have log equals log. Totally different than what we were doing before when we were changing forms. So we'll set our inner parts equal. We're going to have to multiply both sides by x minus 4. On the left, we'll get 2x plus 1. On the right, we're going to have to distribute. We get 3x minus 12. We need x on one side only, so let's subtract 2x on each side. And then last thing you do is add 12 to both sides. You're going to get 13. And if you plug that in, you'll find that it does work. All right, and that's going to be it for this video.